Hello guys, welcome back to Engineering Hack, where we solve engineering problems in a way that's hopefully easier to understand. Today we have a classic problem on thermodynamics, a problem with the piston that can move without friction up and down, and the stops. And these stops here are not going to allow the piston to move as soon as it hits it. So let's read the problem statement. 4 kilograms of water at 15 degrees Celsius are contained in a vertical cylinder with a piston with no friction, which has a mass such that the pressure of 700 kilopascals is exerted on the liquid. So that is the weight of the piston plus the atmosphere, that's 700 kilopascals. Heat is transferred into the water, causing the piston to rise until it reaches the stops, where the cylinder volume is 0.86 meters cubed. More heat is then transferred to the water until it reaches a state of dry saturated steam. So that's the same thing as saturated vapor, okay? We are to determine the final pressure, the heat transferred throughout the whole thing, the work done throughout the whole thing, and to show the process on a TV diagram, that V being for a specific volume. So I drew the problem here. We initially start at 700 kilopascals and 15 Celsius. How do we know that? Well, the 15 Celsius was said, but the other thing that was said is that we have a pressure of 700 kilopascals pushing down on this, right? And we know that what's going to happen here is that this piston, because it can move without friction, is going to be pushed down until the pressure inside the steam is the same as the one that's pushing down on it, right? So it's going to find equilibrium when both pressures are the same. So when we have 700 pushing upwards and 700 pushing downwards, then it's going to stay still. So we can be sure that this is 700 up, 700 inside as well. And then I'm going to start to add heat. And as I add heat, what will happen? Well, as I'm adding heat, this guy here is the steam is going to gain energy, and it wants to expand, right? But it doesn't have enough force to expand. So the pressure will increase. And the pressure is going to go to 705 or 701, a pressure that's above 700. When that happens, well, then the force pushing upwards is greater than the force pushing downwards, which means that the steam can expand a little bit. But once it expands, the pressure drops again to 700, right? And we're back to where we were with the two pressures pushing up and down, but now with a bigger volume. Same thing, as long as the heat is being added slowly, same thing's going to happen. More energy is going to come through. This is going to increase in pressure until we can push upwards, and then it's going to go upwards like so. And then the volume expands a bit. The energy is used in the form of work for it to expand, and the pressure is back to 700. And that's going to keep happening until my piston reaches those stops there, right? So because this is happening with the pressure kind of staying always at 700 kilopascals, this is considered an isobaric process, right? That is a process that happens at constant pressure. Because note that my pressure is always varying around 700 kilopascals, right? It goes to 701, back to 700, 700.5, back to 700, and so forth. So I can be sure that by the end of this process, when it reaches a stop, the pressure here has to be the same as the pressure in the beginning. So that also has to be 700 right here. Let me make this a bit thinner. So this also has to be 700. Yep. And we know the volume is 0.86 meters cubed. That's what's been said to us in the problem. But then at this point, now my piston cannot go upwards anymore, because it doesn't matter how much greater this pressure is in relationship to those 700 that we're pushing down. Now we have two stops. So these stops are going to exert a force that's contrary to the piston trying to push up. And it doesn't matter how, as long as these stops can stop the piston from going up, it doesn't matter how much pressure we have pushing upwards, we're going to have those stops literally stopping this from going upwards, right? So that means that the volume can't change, right? And the volume, if the volume can change, what's going to change is the pressure, right? I'm going to have an increase in pressure inside my steam here until the heat addition process is finished. But because this piston cannot move upwards, then we know this is going to have the same volume at the end of the process, right? So this is an isochoric process, right? Also known as an isovolumetric process, depending on where you guys are. Okay, so isochoric or isovolumetric. So we can be sure that this is a saturated vapor because it says so in the problem statement, but we can also be sure that this volume here is the same volume as V2 on state 2, right? So this is 0.86 meters cubed. And this is always going to be the situation when we have a problem with the stops. And you'll see this problem at some point when you're studying thermodynamics. This is always going to show up. Okay, so note that we have two things for each of the states. On state 1, we have pressure and temperature, all good. On state 2, we have pressure and the volume, and we also have the mass, so we can find specific volume. And on the third state, we have a specific volume for the same reason, and we also know it's a saturated vapor. So we can define all these three states, and we grab any thermodynamic properties for all these three states. Okay, so I'll be calling this one state 1, this will be my state 2, and this will be my state 3. Okay, the first part of the problem asks what is the final pressure. So what's P3? Right, that's the first question. What is P3? And on state 3, if we look on state 3, we need to find what's that specific volume 3, which is by definition just volume divided by the mass, right? And we have those two things. It's 0.86 meters cubed divided by 4 kilograms, and that is 0.215 meters cubed per kilogram. Okay. With that, knowing it's a saturated vapor, what we need to do is just look on the steam tables and find where do we have a saturated vapor that has 2.15 meters cubed per kilogram at a on the water table, right? So saturated water, looking at a pressure table, and I'm looking for a specific volume in which the saturated vapor is 0.215 meters cubed per kilogram. And you see this is close enough, right? This is not 0.215, but it's approximately 0.215. So that means that my state 3 is this guy here. Let me highlight this whole thing here. Right? It's this guy here. Its internal energy is the saturated vapor one, so this guy here. And we can find any other property we want. So that's quite straightforward. The pressure 3 is 900, right? It has to be, because if that guy's a saturated vapor, then the pressure has to be 900. So very straightforward. What is the pressure? Final pressure. Oops, what's the final pressure? Final pressure is 900 kilopascals. Approximately, right? Let's do approximately, because we know it's, because the actual specific volume is 2.1489, but 900 is close enough. So that's our answer for part 1. Now part 2, B, determine the heat transfer and the work done. So it's going to require a bit more math, right? So the first thing we need to know is that if we have a isobaric process, then we know that when it integrates PdV, our pressure is going to come out of the derivative. So that's just going to be pressure, the 700 kilopascals, times the difference in specific volume. The specific volume on the second guy here, we already know. The first one we don't, but we can find out. Okay, so we can find the work by finding specific volume or on state 1. The other thing here is that the work on this guy is nil, right? 0. Why is it 0? Because there's no change in volume. If there's no change in volume, the dV here is 0. If that dV is 0, work is 0. So that means that to find the total work, all I need to do on this problem is to find what is my specific volume on state 1. Let's go ahead and write state 3 here so we don't get confused. State 3. So what I'm going to look now for is state 1. And what I know that state 1 is at 15 Celsius and at 700 kilopascals. So let's go ahead and look at a pressure table. I'm looking for state 1 now. I'm looking at a pressure table, and I'm going to look at 700 kilopascals. And I'll note that the temperature at the 700 kilopascal saturated temperature is 164. And my temperature is 15, right? So because my T, so T1, is smaller than the 165-ish, approximately, then I know that this is a compressed liquid. Right? We have compressed liquid. So as long as, and if you might not remember this, but as long as my pressure is smaller, if my pressure is smaller than 5 megapascals, then I can approximate my properties to the one of the saturated liquid on the temperature table. This is quite important because if we do the pressure table, that's going to be associated with a large error generally. So we need to look at the temperature table. We're looking at 15 Celsius, and we're going to grab our properties as being the saturated liquid properties because our pressure is smaller than 5 megapascals. If it were greater than 5 megapascals, then we have to look at the compressed liquid tables. Not the case. Okay, so I'm looking now at the temperature table as opposed to the pressure table, still for saturated water, and I'm going to go to 15 Celsius. So I'm looking here, 15 Celsius. And I'm telling you that the specific volume can be approximated to the saturated liquid volume. So do this. Specific volume 1 is approximately equal to EF, which is 0.001. Oops. Okay, so with that, we can go ahead and calculate the work, right? Because work from 1 to 2 is the integral of PdV as we go from 1 to 2. And because the pressure is constant, that's just going to be P delta V. And in that case, that's 700 kilopascals. And then the volume, the final volume is, what's the volume on? It's 0.215. 0.215 minus 0.00001. That's meters cubed per kilogram. So we're going to have an answer in kilojoules per kilogram. And I got this to be about 150, so approximately 150. Okay, so that is, and let's just do a little extra bit here. So because work from 2 to 3 is 0, then total work equals 150 plus 0, which is 150. And if we want to consider the mass, then we need to multiply that by. So total work also equals 150 times 4, which gives us 600 kilojoules. Right, so that is total work. That's also total work. Cool. Now we got work. Now we need to find the heat, right? And what's the heat as well? To find the heat, we're going to have to apply the first law of thermodynamics. Because let's go back to our drawing. Where's the drawing? Here it is. Okay, because we know that the change in internal energy has to be equal to heat in work, right? If we know we found the work already, if we find the change in internal energy, then we can find the heat for each of the cases. So to do that, my game plan is I need to find what's internal energy 1, internal energy of 2, internal energy of 3. And then once I have that, then I can do UU minus U1. It's going to give me delta U for the first process, and U3 minus U2 for the second process. Okay, so let's go back quickly on our state 3, and let's grab U3. That was the saturated vapor, so internal energy, it's already highlighted there. U3. Great. So that's done. Let's write that down somewhere here. 2579. All right. Now we need U2 and U1. We were already looking at state 1 here, and we found it to be saturated. So that's good, because that means we can go and grab it straight off here, right? For the same reason as we grabbed the specific heat. So U1 is approximately equal to UF, which is 62.98. Let's go ahead. You can probably call that 63. I think our life's easier. Okay, and that's kilojoules per kilogram. Brilliant. So all we're missing is U2. And if we get U2, then we're good to go to calculate the heat. U2, remember that state 2, we know 700 kilopascals, and specific volume is the same as specific volume 3, so that's 0.215. Okay, so I can go and look on the pressure table at 700 kilopascals, and then have a look at my specific volume. So we're now looking at state 2. Okay, and I'm looking at 700 kilopascals, and I know my specific volume is 0.215. And note how that falls between these two guys, right? So we can do, because my specific volume 2 falls between these two guys, then I know this is a saturated mixture. If it's a saturated mixture, then I can calculate my quality, right? I can calculate how much of vapor I have and how much liquid I have. To do that, what I do is the property that I have minus HF, which is 0.001108, divided by the total thing. So that's the specific volume for the vapor minus the specific volume for the saturated liquid. And that gave me about 78.73%. Okay, so that means that if I want to grab my internal energy, let's highlight the internal energies. All I need to do is I need to take 78% of this guy here and the remainder of this guy here. And then I'm going to have my internal energy. So let's do that. So let's do it over here so we can see the values. If I want my U2, then all I have to do is 696.23 plus X 7873 times the difference, which is 1875.6. So my U2 is approximately 2,172.9 something. So let's just go ahead and call it 0.9. Brilliant. So now I have all the delta U's that I need. I have defined all the states. I have all the properties that I could have needed for this to solve this. Let me go ahead and grab those so that we have them all ready to go. So I'm going to grab this one here, my U1, copy. And where's my, that's my U3. So let's put that way here. Cool. Now with this gang here, what we can do is, as I'm going from 1 to 2, I'm going from 1 to 2, my delta U, let's do that in blue, my delta U has to be equal to Q and work, right? What happens to my delta U? Let's have a look. Delta U is U2 minus U1. U2 minus U1 is going to give me 2109.9, right? So I'm just taking this guy and subtracting this guy. That's all I'm doing. So I've increased my internal energy going from state 1 to 2, right? And I've also expanded, and that required me to use 150 kilojoules per kilogram. So if that's the case, then it means that the heat that I need to add needs to be able to account for that. It needs to account for this increase in internal energy and the increase in work, right? So that means that the heat, so therefore the heat I need to add has to account for the 2109.9 increase plus the 150 that were required for the gas to expand all the way until it hits the piston, no, the stops, right? And that gives me 2259.9 kilojoules per kilogram. Great, so that is the heat added from 1 to 2. What about from 2 to 3? Well, from 2 to 3, my U, let's change colors to black. U3 minus U2, that will be 2579 minus 2172. And that gives me 408.1. So again, I got an increase in delta U, right? Which is kind of obvious because I'm actually giving energy to that guy and there's nothing being used in the form of work, right? Because we know work did not change. And then there's no work, right? Work is 0. So in other words, we're trying to answer the question, delta U rose, where did the energy come from? Well, that energy came from heat, right? That's the energy being supplied to the system. So that means that this guy has to be equal to 408.1 kilojoules per kilograms. What is the total heat? Well, total heat is Q1 to 2 plus Q2 to 3, and we also need to multiply by the mass to get it in kilojoules as opposed to kilojoules per kilogram, right? So that will be, let's put the mass here as well, mass. So total heat will be 2259.9 plus 108.1, and I'm multiplying the whole thing by 4, and that's kilojoules per kilograms times kilograms. So total heat ends up being 10,672. And that is kilojoules. So that is the answer for total heat. Okay, so did total work, which is 600 kilojoules, total heat, which is 10,600 kilojoules, and the part C is the one that asks us to do the PV diagram, I forget. TV diagram, right? So we want to do the TV diagram. So let's jump down. I have it preset. Okay, so I drew the dome here, right? This is the line that separates, this gives us the saturated liquid line. This is the saturated vapor line. And we know that in the beginning, we have a compressed fluid, right? State 1 is a compressed fluid. It's at 15 Celsius. So it has to be outside in this region here, outside of the dome, right? So let's go ahead and put it here. Then we raise until we raise the temperature. We go give energy to the system until we finally get a saturated liquid. We don't really know at which point this happens, but we know at some point it has to happen. And once that happens, then we know we're going to follow a straight line because the temperature cannot change while the thing is expanding, right? It's using the energy to expand. And then at some point here, it's going to stop because it reached the stops. And then from this point onwards, it cannot change its volume, so it has to go straight up, and our temperature and our pressure are increasing, but our volume is not. So this is the path that this guy would follow. Something like this from here to here, and then a straight line here without changing the temperature whatsoever, and then a straight line upwards because it's not changing its volume, right? This is 15, we knew that from the start. This is 65, we knew that from the start. The 175 I got from state 3. So if you go to state 3, or just state 3, state 3, this is where I got it from. Okay, so it's a 900 kilopascals and the temperature is about 175. And then the specific volumes, we can write them all down. The first one we know this is the one that's approximately equal to the saturated liquid one, right? And that is 0.00001 right there. This one is the one that we calculated, right? This one we calculated from the start, so that we got the 0.86 and then we divided by 4, and then we got 215. Voila. And then this one here, we haven't really calculated it, but we can find it out because we know that this guy is a saturated mixture there at 165, so we just need to grab this specific volume of the saturated liquid for state 2, right? And there it is. So that's going to be 0.01108. So this is 0.00108. And there you have it. This is our TV diagram for the process with these stops. Okay, if you have any questions, just let me know. Hope this was useful. If it was, make sure to subscribe to the channel so you're always up to date with our problem solving, our latest videos, and theories being published.